Good afternoon, and I understand we are all tired, including me, so I'll be brief and quick. Okay, this project is on behalf of 4 core members, Ras Taylor, Sri Krishna Shekhar, and my colleague from NCRA, Ishwar Chandra. Ras, we all know. Sri Krishna has just moved to NRO, and I'm talking on behalf of the core team members. And this project is called superMIGHTEE project. It's Deep GHz Universe with GMRT and MeerKAT, a pathway to the SKA. That's how the project was. So the project was built around, you have seen this slide and all the key science projects which are also there in the hardbound book which is given to all of us. And in that there is a MIGHTEE project which is deep continuum imaging of the early universe. And it's built around that. So it was one of the continuum survey projects using MeerKAT. And it focused on 3 or 4 key fields, essentially XMM LSS field, Chandra Deep Field South, LIS S1, and Cosmos field. Together, the survey area was of the order of 10 square degrees at L band with a focus to get 2 microjansky for these deep fields. In addition, there was also planned to have some S band data and the deep L band for one of the field, 1 square degrees, where a lot of amount of time was invested to get 0.1 microjansky. So we are essentially taking all the continuum survey data which is available using using the MeerKAT project and put it together in the MIGHTEE. At this stage, essentially we chipped in, we thought why not GMRT as well in this project, and GMRT was upgraded. So what I'm showing here is a one primer describing what the upgrade is all about. This little patch over here is occupancy of frequency and the bandwidth around that central frequency. When the GMRT was available as a legacy instrument, and when it was upgraded, this became 70% for the band 2, similarly around 70% for the band 3. Band 4, it was roughly 40%, and band 5, which is L band of GMRT, 2% became 30% or so. What you see over here in the yellow is essentially what MeerKAT occupancy is. So if you look at it in this manner, it's fantastic, large frequency occupancy. We have continuous frequency coverage all the way from the 120 megahertz to 1.8 gigahertz almost. These are the upgraded feeds of GMRT. And we essentially had fantastic complementarity in the sense that you have dense core and 8-kilometer long baselines in the MeerKAT. Factor of 4, you switch it over here, you have 25 kilometer and a dense core at GMRT, and we are operating at factor of 4 less in frequency, so you essentially compensate the angular resolution exactly. We have also looked at the UV coverage for very sweet spot of fantastic declination range. For a 5-hour observation, both MeerKAT and UGMRT gives you nearly identical UV coverage, which is telling us that we are sampling similar spatial scales. In addition, this is talking about the sensitivity. What you see on the y-axis is RMS sensitivity and the frequency. For a typical 9-hour observation, the upgraded GMRT points are these magenta ones over here. Band 3, band 4, band 5. This little piece over here is the MeerKAT up sensitivity. And if you look at the sensitivity of these 3 bands, MeerKAT and band 3 and band 4 of GMRT, band 2 is sitting over here, you have identical sensitivity all the way from band 3 of GMRT to L band of MeerKAT. So with this, essentially we asked a question, okay, can we take the all data for the MIGHTEE fields and ask a question, can the combined data sensitivity with the aim to get microjansky levels from 0.25 to 2.7 gigahertz with well-matched resolution? And essentially you then have spectral information for all of them. We are also keeping the data in the polarimetry mode. So we'll be looking at the Faraday complexities. And this essentially is important in the sense that suppose you do Faraday rotation measurements for the deep field sources in the deep fields only using MeerKAT. And to that, if you add the UGMRT, you increase the factor of 3.2 times in terms of sensitivity and the frequency coverage. So essentially, it's important for complex polarization or repolarization, you name it. And in addition, for the 10 square degrees fields, you can essentially take sources for large redshift range, stack them, and give you better constraints about the star formation rate, etc. Also, if you ask where does this fit in the amount of area sampled as a function of sensitivity limit of various surveys. This is kind of the limit of all the good surveys performed till today, including Cosmos, LIS, N1, etc. And these are the SK pathfinders which will fill up this parameter space, and superMIGHTEE will be sitting somewhere here. Low in area, collecting area, but much deeper in sensitivity. So with these thoughts, we essentially planned a pilot project. This was essentially in mid-19. So we essentially had 4 pointings at band 3 and 19 pointings planned for the band 4 observations of GMRT. So these are essentially, red ones are MIGHTEE datasets, blue and the green are band 3 and band 4 respectively. So we got this thing and we got some, so it was PI driven project, and we asked what are we seeing in these deep images using GMRT. And these are the deep images, band 4 and band 3. You have 8 microjanskis and 20 microjanskis limit. We were very happy. This essentially is from the PhD project of Emmanuel Okran, who essentially came up with this distribution of radio loud and radio quiet AGNs. What is it telling us? What the spectra of these AGNs telling us? This is what is shown, radio quiet and the radio loud distribution, and then the spectra of these, and the median spectral index was 0.73 for all the detected sources in band 3 and band 4 of GMRT. Essentially, the thesis and its thesis told us that up to a redshift of 1, most of the brighter sources are dominated by star-forming galaxies. At this stage, we said, okay, we have a data. Are people looking for science drivers using this data? And we had a big list over there. Some galaxy clusters in this thing, interaction FR1 in the, etc., alignment of radio galaxies in these fields, so on and so forth. We were also, but core team was more interested in looking at the calibration imaging because we were looking at more data along the time. And are we going to be limited by various factors? So at this place, we essentially called the project as Joint Exploration of the Deep Radio Sky with MeerKAT and GMRT, the pathway to the SK. This was essentially India DST and South Africa NRF project, which was funded around the same time. So we essentially, I showed you this thing. This was in late 2019, and what we have done today is the following. We have essentially UGMRT data at band 2, band 3, band 4 of these, for these fields, and MeerKAT data is already there, which is complete. This little 16 over here is going to become 32 or 40 soon because we have approved proposal for this field. So now we are talking all the way from band 2 to L band of MeerKAT, a contiguous frequency coverage for all these fields except LIS S1. This is one of the preliminary results. What this plot is showing, the temperature plot, essentially spectral index at low end of the frequency and spectral index at the high end of the frequency, and ask a question, how is this segregating all variety of sources? These are color coded. Black ones are brighter sources, red ones are fainter sources, and cyan and green are in between the two. And these are essentially put into the 4 quadrants, essentially conventional steep spectrum sources, flat spectrum sources, inverted spectrum sources, and the, inverted spectrum sources and the regular opposite end, V-shaped sources. So at this stage, we also came to know that this is the same field which I showed you earlier. These little pieces are where we are going to be limited by direction-dependent errors. So we have to correct for this thing if we want to do the polarization part in the field. This is a primer about what the data looks like. Essentially, you have, this is what you want, this is what you have observed, and these little pieces, please bear with me for this one slide. You essentially have some measurements. These are gains of antenna, weights applied to each data. These are direction-dependent errors, which are over there. And you can also have a primary beam, which are, these are 30 stations for GMRT, and you're assuming all primary beams are identical. So there can be errors because of that. And of course, GMRT is spread over 25 kilometers. They are definitely not planar. It's a coplanar, non-coplanar baselines. So you can translate this equation into this. Next step is essentially your AIJ, which is nothing but the convolution of 2 antennas. And A is nothing but the aperture illumination pattern of the antenna. If you have this information, then your polarization is in good control for the whole field of view. This recipe, this slide is showing the recipe, how it is done for the NRO VLA stations. This is the data which is there for how the main lobe, first side lobe, second side lobe, third side lobe, and you can translate the Fourier inversion of that to give you the aperture illumination pattern of the beam. Once you have that, you can correct for this thing. This technique or methodology or recipe was used for the MeerKAT data by same idea group by Krishna under Russ Taylor. And so you essentially have main lobe, and you sample as many side lobes as possible to construct a fantastic aperture illumination pattern. We are replicating the same exercise for the GMRT. This is the first step. Essentially, we have the beam parameters, but we are just going up to the first side lobe. We need to go to at least third side lobe. And once we have it, we'll fill up this space over here. So once we have it, we'll be in a position to talk about the polarization part as well. Having said this, this doesn't mean that we haven't done anything in the polarization front. This is the source in the field, cosmos field, a radio galaxy, where this is the MeerKAT data, and this is the UGMRT band 4 data. What you see here is the polarization position angle vectors, and the contours are polarization, strength of polarization. In both these, the top lobe is essentially more polarized compared to the bottom lobe, essentially telling that the top lobe is towards us, bottom lobe is far away, and bottom lobe is experiencing more magnetoionic medium as it traverses this, hence it is less deep, less polarized. Sure. And moving from here to here, this is largely from the rotation measure. Basically, there is some evolution of the thing. So this is a discovery in the sense this is a FR2 radio galaxy associated with this Y source at a redshift of 1.35. Next, if we supplement UGMRT and MeerKAT, I said by factor of 3.5, you improve the whole thing. This is what I'm trying to explain it over here. The Q vector and the U vector as a function of lambda square. If you sample only the MeerKAT data, this is what you'll be filling up. But if you fill up the GMRT part also, then this is what you'll be filling up. And this pattern is necessary to understand the full parallactic angle correction. And this is what your other, so these are various QU parameters, the PA position angle parameter, and the amount of percentage of polarization, and Q versus U plane. Having done this thing, we took up the next exercise. Okay, in the field of view, can we do the same thing? So essentially, this is telling me that intensity as a function of frequency at band 4 of GMRT for a source. And this is the Q and U parameter for the background source in the same background, which is telling it's more noise-like. And this is essentially different color-coded, where you have I, Q, U, and V. I is essentially polarized intensity over there, and you have the whole information. And then you can construct the rotation measure synthesis. And that is what you see over here, that around 15 Faraday depth of 15 rotation radians per meter square, we clearly see a signal over there. Now I can do this whole thing for the large field of view. Sorry, I had switched off this thing largely to show what I want to feature. I'll just take a half second. In this, if you can see there are red circles and green circles, which have essentially telling that there are a variety of sources with negative RM, positive RM, and the size of the circle is telling me the strength of the rotation measure. And you can do this for the MeerKAT MIGHTEE data. The same recipe, if I apply to the superMIGHTEE band 4 data, we have the similar result for a variety of sources in the same space. So we are almost there. We have a large team who comprises when we submit the proposal. Now we have expanded the people who want to take up various science drivers using this data. And these are some of the PhD projects. These are students who were PhD and now moving on to the next level. These are faculties who are taken up the project for their respective PhD students, and these are still the remaining technical aspects which we want to address. So to summarize, the superMIGHTEE project is an exemplar in the sense that big data and radio astronomy. We have ultra broad, deep, full Stokes survey for some of the fields of the order of 10 square degrees. We provide two key products, continuum science data products, where essentially you have RA deck and the spectral index information, and the polarization product, where you have additional polarization information. And on behalf of superMIGHTEE core team, I thank all of you for attention.
Thank you, Dharam.